Hi, how are you all doing? So welcome to the second episode of the Embedded Hour. I'm glad you could all make it today on such a sunny day in the UK as it is anyway. We've got a few things to run through today. We've got a couple of great speakers to come and talk to you and give you some good examples of what they're working on in the embedded sphere. First, I really wanted to just run through a couple of general announcements. You know, we want to thank you all for coming back, and especially thank you very much for joining last time as well. I'm even happier that you returned. That's always good. What I really want out of these sessions, as I said last time, is to really feel like a community and to share projects and to ask questions. So please feel free what we'll do is we'll do the presentations and then we'll have some time at the end to do some questions, and we can ask questions about what was presented in those presentations, or maybe even something completely different. And if, of course, as well, if you want to come and talk and present about your project, then please drop me an email. I'll give you the email address at the end. That'd be really wonderful. Obviously, everybody's welcome here. You know, whether you're a professional engineer or whether you're an enthusiast, you know, there's really something for everybody, and we all never really stop learning. So that's really good. What we're going to do is I'm going to record this event, so this event's recording, and we'll make it all available to everybody afterwards, so as you can watch it and catch up. We'll have a post-event survey, but if you can take that, that'd be great, because that way we can obviously improve what we're offering. So I don't have a slide to talk about it, but I thought I'd give you a little bit of a rough idea as to what I've been up to in the last month in the sort of the embedded world. So it's been quite a busy month for me. Unusually, the lockdown's been really quite busy, actually. So I'm not sure how I ever found the time to do so much traveling that I did before. But I've been working last month. Actually, it's really interesting today that we've got a guy from Xilinx, Cathal's here talking about PYNQ. But my last month actually has been really quite PYNQ dominated. Working with a customer actually in Northern Ireland on a PYNQ project, on a PYNQ imaging project, where we wanted to get a good few thousand frames per second imaging, and PYNQ really was quite useful to that. Obviously, if you follow me on LinkedIn or Twitter, you're gonna have seen the few projects I've put on Hackster as well over the last month, and some of those use PYNQ as well, and you know, to monitor actually particularly in this COVID times. Although I didn't do it with COVID in mind, but it was on my list of projects to create. You know, we created a heart rate, oxygen saturation monitor, which was actually the first time I've ever actually done any sort of measurement of oxygen saturation. So it sent me down a nice internet learning loop as I was learning about the equations and how it actually works with the different wavelengths of LEDs to measure the different types of hemoglobin in the blood, and then to be able to work out what the saturation was, and to actually then be able to post-process that signal that you receive back, and post-process. And we did post-process that signal that we received back using PYNQ. So that's a really good example of how you can easily capture signals and post-process it. I've been doing a lot of webinars as well. So we've been doing webinars on the M1, the M3, the ARM M1 and M3, the Design Start webinar. So if you're interested in how to get those up and running in FPGAs, then drop me an email, or maybe I'll do a quick session at it in one of these embedded hours, and we can have a quick talk about that as well. But it's been really quite useful. So I'll stop talking about what I've been doing, and we'll move over to our two guests today. So we have, and I'm really going to apologize for my pronunciation of the names to them in advance. So we have Ilias Alexopoulos, who's from Cyprus, and he's going to talk to us about he's going to be our first talk speaker today, and he's going to talk to us about a compact heterogeneous embedded platform system that he's created. And this looks really quite exciting. And then we have Cathal McCabe, who's from Xilinx. I'm sure many of you are familiar with him, and he's going to talk to us about PYNQ. Now, both of these chaps have actually got demonstrations, I'm told, and got as well as having some slides and demonstrations. So what we'll do is we'll run through the talks. Ilias is going to start first, and then Cathal's going to speak next. So without further ado, we'll get Ilias up to give his talk. I'll just give over control of the screen to him so as he can actually start working on it. So I'll stop sharing my screen momentarily. And what I will say, actually, if you've got any questions, you can unmute your microphone and ask those questions, or you can ask me in the chat and answer, and I'll keep an eye on that, and I'll read them out if you can't speak. But Ilias, over to you, sir.
Hello everyone. Let me introduce myself. I'm an embedded systems engineer for about 20 years. I worked in different industries, semiconductor, in startup companies, designing chips sometimes, other times mostly doing testing on digital prototypes for ASICs or for radios. And I have worked with also for product development for different kind of things like cash registers or vending machines. Recently, I'm founder of my own company, trying to do Internet of Things and edge computing. And I also participate in a MARISense program, which is a government-funded program for marine applications, which I will show you how I'm going to use this the platform I have created. Okay, the agenda is the introduction. We did the description of the platform. We'll go forward. So let's start with embedded landscape. I guess the majority of the people who work on embedded systems, they know that the main tools are the microcontrollers. And of course, these have some limitations on the pinouts, or the ports, or the peripherals they have, because sometimes, although they have a bunch of peripherals, you cannot use the combination you want sometimes. And there are other limitations that makes things, depending on the application, of course, things a little harder. Then some companies like Cypress, for example, they have some microcontrollers that have some logic, which is not necessarily like an FPGA fabric, but something similar that can do various nice things, actually, and allow the designer to be more compact. Then we go to the recent, let's say, trend of Raspberry Pis and this kind of platforms, but actually they're not microcontroller based, they are CPU based. So you have a processor that is attached to memory devices and other things, so it's more complicated. But it is very useful because everybody can write easy an application that run on Linux, and everyone can write a program on Linux now. I mean, it's not, you don't need embedded skills to do these things. And then we go on the high-end devices like the Xilinx Zinc or the corresponding Altera or Intel devices, which they integrate a microprocessor with a FPGA fabric. And these, of course, are really high-end devices and require, again, external memories and stuff to work. So in general, all these things require a high level of technology to create, especially on the PCB side, and how you are going to solder things, etc. Of course, there are other technologies emerging now, like for neural network chips, etc., or GPUs, but all these fall under the same, let's say, category. For the embedded systems, usually the most important thing is the real-time performance. We need something that with a deterministic response, not necessarily fast, but to be precise on when things can be done. Sometimes we require low power, especially for the Internet of Things devices where they are remote and we don't have too much power. We need reliability, different kind of features. That's we have a diversity of features we need. And of course, sometimes we need the hardware to be in custom forms. So you cannot take a ready-made module because you need to modify it to have the shape or size you need. And there are some cases that you don't need real-time, like when, for example, you measure temperature, you don't need real-time performance, so you can use a simple Raspberry Pi, which is probably cheaper than using microcontrollers in some cases. I have seen this gap actually around 2002, 2003. I was always thrilled to use FPGAs from the 90s. And back then I was working with the AVR microcontrollers. And I combined this with the Spartan FPGA. Now, the problem with this interlinking these two is that the AVR has a small amount of pins, so it didn't make any sense to connect everything to the FPGA to make it work. So what I did, actually, I have a serial link, a synchronous serial link with a 3-wire, and the AVR controls FPGA through this link. Here are some photos you can see that from a robot I tried to do for my daughter once. And it's actually, you can see here the AVR microcontroller, and this square chip is the Spartan FPGA that controls through servos the motors of the robot and some other peripherals we are going to see. Here you have a closer look. It's a more clean photo with some probes on it. Now let me switch to video and show you this in action. Okay, here I'm connected with a serial port to my board. You see that I control through a terminal the grip. I don't know if this is visible. Also a sensor, an IR sensor, distance sensor that moves, and its purpose was to figure out the distance of any obstacles. The wheels of the robot, the turning, and I guess this is now the throttle. You will see the back wheels moving. So I think here, okay, this is a code. Let's go. Let me show you how fast it was to compile. So I was this is my editor. I understand that you don't see anything meaningful here. It's just it's the interface. It was a lower resolution video back then. Here I compiled the program. You see in a few seconds I could compile it. And I'm downloading to the hardware. So I did a modification of the software to make the motion smoother. And here you see the terminal, as much as you can see, that I control the system. So now, for example, you see how the grip works better and shows you how it grips a pencil. All right, so let's go back to the presentation. Where we are here. So let me explain a few things how this worked. So first of all, we have the configuration of the chip that needs to be held in an external memory. But because I didn't want to have an external ROM to store this data, I had made a script that converts the bit stream of the FPGA to a C file that includes on my software that I write on the microcontroller. And the system, I have a small round-robin system, not something fancy. You can find this on Code Project if you want. I download this bit stream to the FPGA. Then the FPGA code is active. The FPGA code in this case is something like that. It has a simple serial interface with registers that are accessed through the serial communication bus, and have some register for controlling the servos. So this is servo control, doesn't matter. We have many channels. In this case, I had 8, but I could do more than that. And the operating system or the application, in any case, controls this through this link. This is fine for the 8-bit microcontroller and the low pin count, but I wanted something more. Actually, back 10 years ago, I was thinking to do a drone before the drones were so common, quadrocopter. Because of that and other reasons, I wanted to create something bigger. So because I was involved with cold-fire microcontrollers based on 68,000, I combined the cold-fire with a Spartan 6 device. I have two versions of the board you can see here. This is a bigger one. This is the microcontroller. This is the Spartan 6, and I have also an SDRAM. I have dual switching power supplies. Dual because I wanted to drive servos, so actually I don't need two power supplies in general. I have also an Ethernet interface, USB, the programmer port, and SD card. And here I have a smaller version, which I will show you afterwards. We will work with something. I will show a simple thing that I have done. So the idea here is, because of the configuration of the FPGA is bigger, I store the configuration file in the SD card. And so the microcontroller loads this data from the SD card, downloads the configuration stream to the Spartan device, and then after the FPGA is configured, we switched to the bus mode where there is a flex, mini flex bus called bus from NXP that is common to cold-fire microcontrollers and Kinetis. So actually we can replace the microcontroller if we need from a hardware perspective. And it's a multiplexing of address and data bus. And in this case, we present the FPGA as part of the peripherals of the microcontroller, with, of course, the corresponding design files. Here is the configuration. Again, so there is the SD card, the controller, the mini flex bus.
So how big was, just one question, how big was the SD-RAM that you have on there? So you said you had SD-RAM?
Yes, doesn't matter. I have an 8 gigabyte, but I use a few kilobytes.
Okay.
The configuration is 300 kilobytes. It is intended to store other things like logs or whatever from, you know, when you install this as a system.
Yeah.
I have actually created an SD card driver myself, and integrated the FAT file system. So from my monitor, I can check the contents of the SD card.
Cool.
I will show you, I think I have a video on this, you will see. So the feature of the system is, okay, the cold-fire runs at 48 megahertz. Why 48? It can go up to 80, but 48 is convenient for USB connections. There's no limitation for this, up to what the chip can do, so I can go up to 80. On the smaller board, because I want to be more cost-effective, I use the same clock for the Spartan, although I can use a different one, of course. I have a 24 megabyte per second link between the two. It's memory mapped, and what we can do, for example, and I will show you later, is that I can memory map devices, not devices, peripherals inside the FPGA, and I have done a case where the stack of because I use also an RTOS in this case to do the framework for this. The stack of the tasks can be on the FPGA, and actually I'm working on something I want to publish on memory protection and debugging, because through the FPGA we can directly see what is going on in the memory and maybe catch like stack overflows or other kind of errors that are difficult to catch with software without having any performance penalty.
Yeah, that's pretty interesting.
Yeah, it's something that worked, but I realized that doing that, I had to overcome other issues because usually the real-time operating system have linked lists, and if it's a linked list of tasks, the task control blocks, that they are not visible at the same time, you have to modify the RTOS to how to transverse this linked table because the memory it's not visible at the same time. So when, for example, I have a pointer that points to another structure, this structure is in a different protected memory, and I have to switch on the correct, let's say, memory to see it. It's another memory page. Anyway, this is something I hope I will finish this year. Yes, the FPGA configuration is loaded from the SD card. The boards are 2 layers. And of course, the design is scalable to larger Spartan X. There is no limitation to use Spartan. I use the LX9 device in this case. The board is big. If you see the board, you know, it's not very big, but if you compare it with a Raspberry Pi, for example, it's bigger. The reason for this is that I use QFP packages, so it's easier for me to debug, because when you do development, you don't want to have BGA devices or, you know, tiny things you cannot probe or check. So my idea was that, okay, this is a development system. I need to develop things. I don't want everything to be tiny. So I need a reasonable, let's say, size that will allow me to develop. And afterwards, if I want to go to production for a product or whatever, I can certainly do everything in BGAs and do it really tiny.
Okay, that's quite cool. So one question just came in actually asking what excuse me, what RTOS you used for the
yes, I'm laughing because probably you will not know it. It's called PYNQ. It's a guy who was inspired by FreeRTOS. The reason I selected is that the code is very clean. It's one of the best in respect with writing style, because for me software is important. And of course it's not the best. I know that there are limitations on this, but actually I'm extending this and adding features and correcting things. One of the things I want to do is to create hardware extensions of the RTOS and, for example, provide the next task to run from the FPGA to be hardware accelerated. So yes, this is the answer. It's PYNQ. And the reason I selected this was the code quality of this.
Okay, so that's PYNQ, so FANK.
Yes, I have written here, I think. Let me see.
Ah, you can get to it. You can get to it when you get to it. If you PYNQ. Ah, yes.
Okay. Okay. The other thing I'm doing is okay. Of course, because it's Spartan 6. Why Spartan 6 and not Spartan 7? The reason is that I wanted a 3.3 volt capable FPGA. And because the newer devices are going to lower voltages, I want something that would be interfaced directly with microcontrollers and other stuff that are common for this kind of applications. The boot time is about 20-30 seconds from the SD card. And of course, I use the ISC tool, so I don't have the luxury to use directly the VTs or the newer tools that Xilinx has. Now, the approach of this is that I want a good quality code, so whatever I run, I develop myself. It is written using test-driven development. I use PPU test as a framework, so I debug everything on my PC, and then I do minimum debugging on the target. And the reason for this is twofold: is that you can, of course, have a safer, let's say, path for the target, but also you have the benefit that if you refactor, you can make sure that previous functionality is not broken, or if you have any, let's say, edge case that it's difficult to create in physical world, you can create it easy on your simulated, let's say, framework on the PC. Okay, let me show you now the SD card. The SD card driver actually was developed with this methodology. The first example here. So this is my compiler of the target. Here I open a serial port. I have integrated a full command line interface on the system, which I have also written myself. I have history, you can go back, delete. Okay,
That's quite cool.
This is what, these are the available commands. And here I will try to mount the SD card. It's mounted, and here you see the data of the SD card. You see the size.
Okay. Yep.
All right, and then let me show you an example with writing the SD card. You see here, let me, on the bottom of the screen, you see I'm writing the numbers 1, 2, 3, 4, 5, up to 8, sector written. I don't know if it is, if you can see it.
Yeah, no, we can see it on the bottom, and you can see it.
So I wrote the first 4 bytes of the sector. Of course, I cannot write all the sector through command line. So the purpose of this test of the command is to test that I am able to read and write the sector. So you see that I'm able to do that. So I zero it out again.
That's pretty impressive.
And the interesting thing you see here on the side, this data, these are from files, actually copies from the SD card. And these are used as test bench in the test bench for the SD card driver. So I actually used real data to test the software.
Ah, cool.
For the FPGA now, I use a GHDL simulator. It's open source, and GTK Wave and UVVM framework, where I created a mini flex bus functional model. And then I create register there, and everything is up to after that. So I add IPs after on top on that. So there is a full framework on that already.
Okay.
The tools, of course, are the usual: oscilloscopes, serial ports. And let me show you the main card, the big card, when it's configuring. So the controller works anyway, it doesn't need the FPGA to work. Here I define the file name. You see on the bottom, I'm actually writing a path. I can actually read any file. I can see it on the monitor, on the SD card, or have a directory. So you see, as soon as I press the button, this LED went green. This is the done pin of the FPGA. So, okay, I can speed this up a little. It's I'm waiting in real time here. At some point, the configuration will finish. And you will see, you see the done pin went low, and now actually the software is already running and writing the registers that you see the LED.
That's pretty cool.
The interesting thing is that this FPGA uses a 133 megahertz crystal. So the two clocks are asynchronized. So I have a clock domain crossing here. And one of the tests I did, because it was the first time I tried this, it was the first time I made a stress test to make sure that the registers were always written and see that the design was performing as expected.
Yeah, CDC can be a real issue, a real challenge to get working.
So let me now show you an example. I have here my system already running. Maybe I can restart it, but I'm afraid I will have to reconfigure again.
Let's try it, otherwise, because we're slowly running out of time. So let's try this, and then we'll hand over to Cathal.
Okay, so I will just run the code. I have already compiled the code. Maybe I can show you where I will put a breakpoint. Let me see. Okay, here is my FPGA task. So when it starts, the first thing it does, it's a very simple. I have actually more a better version of it than another file, but I think this is will do the job. So the first thing I write the command line that actually I would write myself on the monitor. This is the command FPGA probe, and then here is the path.
Okay.
So I can select any file on the SD card. Because previously I had this one. Now for this demo I put the newer one. And this command actually executes this string, and this configures the FPGA. And then in this command, we revert the bus from configuration state to actual working state, so we can access the registers.
Okay, so let's give it a try and see what
sure.
See what happens.
So let's go. Relaunch. Okay, we're ready. So I have put a breakpoint here.
Look at that.
So let me maybe put the camera and show you the actual board. See, I don't know if you see it.
Yeah, we can just about see the board now. Yeah.
And let's go. So I have a.
So I just saw the LED come on.
It's already the LED now. The done is high. So we are downloading at this moment. You will see exactly the same as before, but in this case we are going to access the registers, and you will see it, that these are memory mapped on the IDE. One thing I have to do is to tell the debugger that these areas actually are valid memories to check, because otherwise it will not allow you to access these areas, because these are outside of the standard memory space of the controller.
Okay. So this has to be the last thing we can see, because actually we're about to run out of time, but I think we can we see the flashing light now?
Yeah, you see it?
Yeah, I see. Yeah, your name was on the video screen just out of the way. But yeah, that looks really cool and is a good demo. Is there anything you'd like to say just to wrap up before we move on to our next presenter? Or?
Yes, one last thing is that let me show you now the memory. For example, this is a memory. I can go here and write. So you see it's written.
Yep.
And also I can see my registers. Of course, it's 16-bit, so I have to format this to 16 bits to be more precise. And the last thing is I have here a version number. So my actually latest code, what it does, it checks this code, and if this is different, it downloads a new firmware, the new configuration file. So you can do also revision control, and the software matches the actual hardware it expects to have.
That's a perfect example. So I'm going to stop you there and thank you very much for your demonstration. I'm sure people are going to have some questions when we come to it. I think it's time now. Cathal's going to give us a chat on PYNQ. So if you could just stop sharing your screen so as Cathal can grab it, we'll be hopefully we should be good to go. So Cathal, over to you, sir.
Yeah, so just sharing my screen now. Are we good to go?
Yeah, we're good to go. Yeah, I can see your screen.
Okay, so thanks very much, Adam. So as Adam said, I'm Cathal McCabe. I'm going to talk about PYNQ. I have a lot to get through, so I'll try and squeeze it in and I'll get straight into it. Okay, so I'm going to make some assumptions. So very quickly, I'm assuming that you're either an embedded or a hardware developer, or at least aspiring. I think that probably is everyone in this audience.
I think so, yeah.
I'm assuming you know a little about FPGAs, or at least a little bit about Zinc. I was going to give you the hint, if you didn't, that Zinc is an ARM processor plus an FPGA, but Ilias has helped me out there. I think he's already covered that. And I'm not assuming that you've heard about PYNQ or Python or Jupyter. I'm going to talk about all those things. I guess my last assumption, I hope everyone here does want to do awesome things with embedded systems, and I hope I'm showing you a framework that might be of interest to you. Okay, so very briefly, what is PYNQ? So PYNQ is a Jupyter-based Python framework. So we're an open source framework to allow us to interact with Xilinx platforms. So what does all that really mean? So Jupyter gives us the ability to connect to a board from a standard web browser. So I'll be using Chrome today. From there, we can connect to any of the boards that are running PYNQ, and we support Zinc, Zinc UltraScale, or FSOC, and actually also Alveo, not shown on the screen here. So we can connect over a network, so either Ethernet or Wi-Fi. Some of these boards have built-in Wi-Fi or USB Wi-Fi dongles. I can either connect directly to a board from my PC, or this could be running over the internet or a local network. So from Jupyter Notebook, it gives me a facility to log in and connect to the board of my choice. So Jupyter is actually running on the ARM processor in my target board. And from there, I get into my Jupyter Notebook environment where I can start to write Jupyter notebooks. So this allows me to write Python code to interact, to control my programmable logic in my board. I can capture the output from my code. I can also add rich multimedia documentation, and I can also use powerful visualization all within a notebook. The notebook also makes it very easy to share and also to reproduce my work. So rather than actually talking about this on a slide, I'm going to show you this. So in fact, this is actually a Jupyter notebook that I'm running right now that I'm sharing my screen. So maybe some of you might have noticed that this isn't quite PowerPoint. So I'm running in full screen mode in a browser, and I'm going to just go out of full screen. I'm hitting F11 here to prove it. You can see my little note to myself. So this, what you're seeing, is actually a markdown cell. So this is a way to add documentation. And if I double click in here, you can see the type of formatting that's available. This is a markdown type language. And I'm going to hit Control and Enter here to execute or to render this cell. So you can see in this sort of a framework that mistakes are very easily fixed, that I can just make a change, render this again, and keep moving forward. So that was Markdown, but more importantly, Jupyter supports code cells. So we can mix live code with, if you like, the documentation capability. So the cell that we see here is a code cell. As I say, I don't mind if you're not familiar with Python. I hope this is fairly intuitive. If you've never seen Python before, I hope you can see that this is just going to print out a message. And this output is actually captured in my notebook. So if I hit save now, I can capture my results, and you'll see why that's powerful later on. So, you know, maybe some people are dating me. So just to prove I really am running on the ARM processor on my board, and I've a board in front of me that I'll show you. You can see the output from the command line here. So let me just do a small switch over. This might take me a second in terms of my webcam. So I'm going to have to get rid of my nice virtual background, and I'm going to swap over to a different webcam. And let me take off my background so that you can actually see something. Okay, so this is the board that I have in front of me. I'm just going to try and move it over slightly. You can see a network cable here. I hope it's green, but maybe the sun is washing it out. And I'm also powering the board by USB. So I'll put that back over
We can,
here.
but we're still just seeing your settings thing on the...
Okay, sorry. Are we good now?
No, you're just still showing your screen.
Okay, so sorry, in my in
the
my video.
Screen, yeah, in the video screen we can see. In the video, yeah, we can see the.
Yeah. Okay. So if you can keep an eye on that, if you can't, don't worry too much about that. So I want to show you what you can do with PYNQ. So I guess the most obvious thing you want to do with an FPGA is actually download a bit stream. So I'm showing you the PYNQ Python code now to do exactly that. So most things in Python, you import a library, in this case, the overlay library, and then you instantiate something, then you can interact with it. Actually, this line all in one is downloading the bitstream to the board. So eagle-eyed may have noticed the done LED might have flashed there and you would have seen the bitstream being downloaded. So in this case, base.bit is something that we provide in the PYNQ image. It's already on the SD card. We call this an overlay, and I'll explain a little bit more about that later on. But base is basically just like a reference design for this board. It connects up some of the I/O that we have, the LEDs, the buttons, the switches, HDMI, other interfaces that we have on the board. It allows you to do something out of the box. So just again to emphasize, I'm only using a browser here, a standard web browser. So you don't need any tools installed on your host PC to do this. So there's no Vivado, there's no SDK in the loop here at all. I could actually do all this from my mobile phone if I really wanted to, but I don't. It's quite fiddly, but this is quite usable from a tablet. You can type and generate your code, or at least run demos like this from a tablet. Okay, so I said the base design contains some IP connected to the peripherals on the board. So let's try to do something useful now that we've downloaded the bitstream. So first I'm going to show you what I think is a really cool feature that we've added in PYNQ. So PYNQ will parse metadata provided with the bitstream. So this lets us interactively check what's actually in our programmable logic. So if I run this cell, it's going to print a fairly long list of everything that's inside the design here. So I'm not going to go through. You can see things like there is some video IP. We've got HDMI in and out on this board. I don't think that's really going to work on this sort of a demo. So I'm going to focus on the simple things. We've got buttons, LEDs, and switches on the board. So, okay, let's try and use the LED. So if I do something like this, the buttons are here along the top, if you can see it in my video, and I'm not pressing any of the buttons. So when I execute that cell, I get a 0. But if I press one of the buttons and hold it down and execute that cell again, you should see I'm getting, a real value back from the board. And if I pick a different button, you can see the same thing here. So I can execute the cell multiple times and read back something different from the hardware. I can also make this code a little bit neater. You see I've got a nice read function for my buttons over here. So I guess this is the benefit of using a language like Python. Okay, so maybe just to extend that a little bit, I'm going to get some slightly nicer handles for RGB LEDs that are on this board, and then all the LEDs. And I'm just going to write a pattern. And again, I hope you're seeing something on the video on my camera.
Oh, yeah.
Just to point out that this is interactive. So if I type something different in here and execute again, I hope you saw that flash in a slightly different way.
Change, yeah.
Yeah, cool, thanks Adam. So just a slightly bigger example. So I can't see my board or my camera, so I hope that's flashing away, and I'll leave that in the background. So look, I'm going to move quickly through this. So we can also check and change things like the clock configuration on the board. If you're familiar with Zinc, you'll know that we've got 4 CPUs from PS to the programmable logic. I'm reading back the configuration that's been applied on this board. So in this case, CPU is 650 megs. We've got a 100 megahertz clock. Actually, this one is for the HDMI, which is why it's a slightly odd frequency. And we've got a faster 200 meg clock, and we've got another 100 meg clock in here. So we'll just do a check on that clock 0 again, and you can see that's 100 megahertz. And that looks like a mistake I made, so I'm just going to delete that cell. So again, that's pretty easy to change. I was playing about with this earlier on. So what I've done here, I've applied an 80 meg clock to F clock 0. So you can see I'm getting a warning message here that due to the configuration settings, we can't actually get 80, but PYNQ is telling me we can get to 83.33. It's done some, I guess, some rounding, or it's found the closest value for me. So if I move on and actually check, I asked for 80 and I've got my 83 as close as I can to get to it. So that's really quite cool, particularly if you're prototyping or playing around with some designs. Okay, so to extend this on a little bit, I'm not going to show anything too groundbreaking, but I want to point out here that I'm going to use a different bitstream. So the previous example was using GPIO from the PS. So we're just literally writing down the wires. Functionally, I'm going to show you exactly the same thing. I'm just going to read buttons and toggle, read buttons and toggle the LED values. But this design is actually using AXI controllers, which means I'm writing to registers this time. So if you take this as a proxy for your own design, for your own IP, I'm actually writing into my memory mapped address space now. So, okay, you're going to see an LED blink again, but I hope you can see if you had some higher level functionality or your own IP in here, how you might interact with it in exactly the same way. So I've got a second bit stream on my board, and I'm going to do exactly the same thing and download it. We do have nicer ways of doing this in Python, but I guess I'm doing this from the bottom up, and we can actually read back from the design the addresses where our peripherals actually exist. So these are the addresses that would have been selected back in Vivado when creating this design, and this is a really nice way to verify it. I probably don't want to admit, that I've hard-coded these addresses and you get them wrong and you need to go through your debug cycle to figure that out. It's really nice to be able to do that interactively. So I'm going to import a new library, an MMIO PYNQ library. So this is memory mapped IO. And you can see I'm instantiating it for the buttons. So again, if you know how AXI GPIO work, they can be inputs or outputs. So I'm just going to configure the tri-state by writing all ones to configure this as inputs. So if I go on here again, this won't be this won't be groundbreaking. I'm going to functionally get the same thing again, but there's a huge difference what's happening under the hood. I'm reading and writing into my memory map devices. And again, I'll go through this. I'm reading switches and I'll skip on here. So, this might seem trivial, but I want to highlight how powerful this is. The ability to interactively peek and poke registers, extremely useful for debug and prototyping. I guess it's very underappreciated until the first time you try it or the first time that this saves you. And this is really a fantastic capability, particularly to do from the Jupyter environment. Okay, so I'm going to go on and just, I'll drop out a full screen again. I'll just show you what we provide in our PYNQ image by default. So if we have a look in here, we've got quite a lot of material that's already on the board. I did think about doing some of these as demos for the talk today. Unfortunately, all my little sensors are in a box in lockdown at my office. They didn't quite make it home with me, so I can't actually plug any of them in now. But I think you can get an idea. We've got support for a lot of different sensors. We can plug into the PMODs, the Raspberry Pi interface, the Arduino. Again, I hope even just by eyeballing this code, you can see there's not a lot of it. It's basically 2 lines: import a library, instantiate something, and then read or write these sensors. And you can see, and I'll come back to this, that we can do some nice visualizations inside the Jupyter notebook itself. So I'll just close out of that. Oh, sorry, by the way, I know I'm showing presentation mode for these notebooks, but this would be typically how you would work with your notebooks. You can add more cells, start to write new code in here and execute it. If I put in a real message, rather than the presentation view that you're actually seeing me using this talk. Okay, so I'll jump to, I was going to show you a little bit more there, but maybe in the interest of time, I'll skip on a little bit again. So I have USB connected to this board, but really I'm only using it for power. I could go in, it's just Linux running on this board, so I could get a UART terminal, but I can also do this from Jupyter. So I wanted to show you this. This is quite a cool feature. So I'm just clicking on that link, and you can see that I got a terminal in here, and I can access whatever I want. I'll just show you, if I go into the Jupyter environment, I get exactly the same view, and this is the notebook that I'm working with at the moment, embedded R, and I see the same set of files from this view. So really nice to have that Ethernet-based terminal, if you like. Okay, so I'll skip on. You saw a little bit about this already. I can pass commands from the Jupyter environment. This doesn't have to be PYNQ code. So if I type that properly, you can see I can pass things to the command line and get information back. And again, this is really useful to do to mix Python and maybe mix C code. So I'll show a very quick GCC example here. So I'm just going to run this line of code, and I've kind of put a little comment here. Wait a minute, what just happened here? So I've got a C source file that's on the board here, and I'm just going to more that C file, and you can see this is pretty much as simple as it gets in terms of C code. You can see I like my hello world. So I've actually just compiled the C program above. GCC is on my board. I've just compiled that program, and now we can run it. So again, it won't be too much of a surprise what comes out there, but this is really powerful to be able to compile our C code on the target device that we're working with. So I wanted to show you another nice feature, again, enabled by Linux, and I need to jump around a little bit here. And I have a note to myself that I should have prepared this, and I didn't quite have this open. But I can actually map my board as a network drive. And if I click in here, again, you can see we have a very easy way of transferring files back and forward across the board. So again, this is the embedded R talk that I'm doing, and this is the notebook. This is the Hello World exe that I've just generated. If I delete that and maybe go back just to prove it and build that again, you can see I've just generated. So I could copy files in and off the board very easily here. Okay, so I was going to show you a pip install example, how we can actually take advantage of Python to install new hardware designs. I'm going to cheat a little bit in the interest of time. So this would be the command that I would run. Maybe I'll just jump out for a second. Adam, are we okay to go kind of close to 6 o'clock?
Yeah, we are. Yeah, I'd like to finish about 5 too, just because we've got a few
Okay.
a few questions coming that I'd like to answer. So if you can take like 4 minutes or so to run through it.
Okay. So I'll skip on from that bit. But we have a number of third-party designs, and actually this one's from colleagues in research labs in Ireland. So I can install a hardware design as I would any other software library. This is the output. I'm going to skip this part just in the interest of time. It takes about 2 minutes, and I didn't want us to watch something installing for 2 minutes. So what actually happens during my pip install? So various files have been installed and copied from GitHub, and copied into various places in the file system. So bitstreams, C libraries, Python scripts, example Jupyter notebooks. So these all exist now. I've installed this later on. Something I didn't show earlier on. So if I click in here, we also get autocomplete in here. We also get it for our hardware design. So if we wanted to look at what's actually in the bitstreams or see a little bit more detail on what's in here, we can see the files that exist. There are some example notebooks. Maybe I can go through this very briefly. So I'm just going to click on the link here, and this takes me to the files that have now been installed on my board. So I'm just going to open up this notebook. I thought I might run a little bit, but I'll just show you. So this is actually a machine learning network that's been installed to the board. As I mentioned, this is from colleagues working in research labs in Ireland. So they're taking in a picture of a deer, they're running it through their classifier. This is Cypher 10. They do it in software, they get much better results in hardware. And you can see that you can pull out all the stats from the network that's running, and then you can do some nice visualization on this. So this is all publicly available. It's on GitHub, and you can browse through and read this notebook at your leisure. So I can give out the links for these if people want to have a look for themselves rather than me spend time talking about it now. So let me just close some of these to get back to where I was. Okay. Maybe quickly a couple of examples on widgets. So I mentioned powerful visualizations and capabilities inside Jupyter. And one of the things I really like, I tend to do demos, you can get these widgets. In this case, you can see I'm using a slider to generate a graph, and this is just a simple sine wave, but you can see the interaction between widget and what I'm actually outputting. And then maybe also quickly a matplotlib example. So I'm just generating some, sorry, skipping on a little bit too quickly here. I'm just generating some sample data, and I'm going to plot a visualization of this. So I guess, again, if you can imagine, the extension here would be if you're generating data on the programmable logic and you're reading it back, you can do this type of thing within your notebook and then share it maybe with some other colleagues, or a really nice way to disseminate your information. Okay, I'm on to my last section. I'm back to presentation mode, if you like. So in terms of PYNQ, so we recognize new users will not always be, if you like, hardware designers or embedded system designers. We see more software engineers, domain experts who want to take advantage of FPGAs. And this is exactly what we're trying to do, provide a framework for them to use these devices more productively. More relevant, I guess, for all of you on the call, we also think we offer a rapid prototyping environment for hardware and embedded software engineers. And Adam, you've mentioned you've a bit of experience with this. I hope you're finding it useful for some of the things that you're doing.
No, I find it brilliant for prototyping and bringing boards and designs up. I think it's amazing.
Yeah. So just to put a bit of flesh on what I've talked about and to show you the framework. So, you know, the various Xilinx platforms, and as I say, we support Zynq, Ultrascale, or SOC, Alveo, all have programmable logic. Zincs have either ARM A9s or A53s, so 32-bit or 64-bit processors, depending on the generation. The Alveo boards are PCIe, so we have an x86, this could be an IBM, or even ARM server class processors. We have an OS which is Linux-based, PYNQ sitting on top of that, and then Jupyter at the very top of the stack. So as we saw, Jupyter allows us to connect through a standard web browser and all the things you just saw me do. PYNQ is what enables Jupyter on our Xilinx platforms. In terms of delivery, so if you're working with an embedded board, you can download an SD card image and you could be up and running on this board in a couple of minutes, really, once you've burnt your SD card. For the PCI type boards, we can pip install from the Python package index, PyPy. So again, just a couple of minutes to install and have PYNQ up and running on your data center class board, if you like. And then the final piece, the PYNQ overlays, so those bit streams. Okay, and maybe just, I'm very close to the end, so just to mention, PYNQ is an open source framework. You can see the PYNQ blocks in here, so these are the parts that we provide from the bit streams at the FPGA level. The blue parts are the Linux kernel modules, so things like the Xilinx FPGA manager, and we have PYNQ classes to interact with all of the key blocks here, things like memory management, and then higher level functionality, a PYNQ class, a DMA class to deal with transfer of data. And then of course at the top we have our notebooks. So I'll try and skip through this very quickly. I guess the benefits, and I think we can share these slides, Adam. So you can start using your board out of the box, depending on the platform that you have. If you something supported, a downloadable image. Otherwise, you can port this open source framework to your board, and you get all the benefits of packages, drivers pre-installed, and the ability to add software. We're also Linux, and again, to emphasize and to highlight, this is desktop Linux and everything that we get with that. This is really powerful, the ability to install from the Ubuntu universe, things like SSH, FTP, Samba that I showed you. We can Git directly onto the board. I showed you GCC. We also have a microblaze compiler, so we can cross-compile on the board and target something in the programmable logic. Adam, you mentioned the ARM M cores. It's kind of been on my to-do list and I haven't quite got to it. We could also do something similar for those. So again, no tools required, target an ARM M core or a RISC-V or any other processor in the programmable logic on the target. Again, hugely powerful. I showed you how simple it is to download a bit stream. We can maintain many bit streams on the SD card itself. Again, I talked about debug and prototyping. I'll skip through the last few slides. I realize we're up to time. Analysis, visualization, and installation of packages. So look, if you'd like to find out more about PYNQ, you can go to our website, find out what boards are supported, how to target your own board, documentation, tutorials. So I'll stop. I'll maybe pass back over to you, Adam.
Yeah, that's perfect. Thank you very much. I'm just going to quickly share my screen. We've got a few other questions. We've got a few questions come in, so hopefully you can see my screen now. Anyway, so we've got a couple of questions that people asked. The one was about a PYNQ Z2, and how easy is it to install custom Python packages using pip install? I think you kind of demonstrated that and answered that as you were going through it. Graham, let me just pull up the chat window. Let me just find the chat window because somebody asked some questions in the chat window. More chat. So Graham Smith asked if it was possible to control one or many boards using Python on a PC. If you could do that, so if you could have like a cluster of the PYNQ boards all up and running. Yeah.
So I'm interacting by IP address. So yeah, absolutely, we could do that. Yeah.
And is there a way to ship an integrated overlay that includes all the sort of the bit streams, the C, the Python, and everything? So it kind of
So I didn't get to show that. If you go to our website and find the links to the GitHubs, you'll see how you can package an overlay to do exactly that. You just need a setup Py file that will allow you to pip install. So pip is already included on the board in Ubuntu, and that will pull everything down for you.
Yeah, perfect. Perfect. Is there any other questions anybody else has? Feel free to pop it in the web chat or in the questions window. So Kareem actually says, is there an example design or lab that goes through the entire development process from Vivado to Python?
Yeah, so we focus on the PYNQ side. We have a tutorial I reference on pynq.io. We show you, I think so. We don't focus a lot on Vivado, but I can definitely point people in the right direction for that. I've done a few YouTubes, just some very quick YouTube examples of how to do that, how to take a Vivado design.
So I've done a couple of examples as well on Hackster actually, so I'll put them.
Yeah,
what we'll do is after this, we'll put if you want to send me some links, I'll put an email together that we circulate around to everybody. Yep. So we'll share the links in there. Brendan was asking if there is Ultra 96 support. I believe there is Ultra 96 support for this because I've been using PYNQ on Ultra 96 for a while.
Absolutely.
So I think you can get it for the Z1, the Z2, the Ultra 96, the 104.
104, the RF SOC and Alveo.
And the Alveo cards.
Yeah.
But actually building your own is really quite easy and quite good fun as well. Once you get it doing. And then the last question before we wrap up is Nadeep has asked, how good is PYNQ as an FPGA beginner? Is it a good starting point to get working with an FPGA?
Yeah, I would think so. I guess it allows you to focus on the parts that you want to learn about. You know, if you want to go down to the low level, you can do that. It gives you a higher level environment, makes it a little bit easier to maybe abstracts away, makes it a little bit easier to do some parts, or you don't need to get deep into the detail initially.
Yeah, no, I think it's brilliant for learning. So thank you very much. And thank you very much, everybody, for coming along and for attending. And we will host the next one on the 12th of June, so the next month. So if you'd like to come along and talk, please send me an email to embeddedhour@aduvioengineering.com, and we'll get you on, and you can come and talk just as Cathal and Elias have done today. Thank you very much to both Elias and Cathal for giving their presentations. Really interesting presentations. Really great to see what's out there in terms of PYNQ and what we can do with PYNQ, and what you can do as well when you're sort of designing embedded systems like Ilias is doing, and how he's sort of evolved this system over time. So that's been really great for me to see. But thank you for coming along. We'll send some emails around with all the links to the things that we've mentioned today, so as you can go away and you can investigate them in your own time. But from me, that's all I have to say. So. Thank you very much, and we will see you next month. And again, please, if you want to talk, drop me an email and let me know. Thank you very much. Bye bye.